able to, am I audible to you? Yasin, sir?
Yes, of course. Yes, yes, you're audible. Yes.
So, Syed Yasin, he's a chief scientist in artificial intelligence and machine learning at Safersoft Technologies. He was AI mentor, director, and founder at Brookle Innovations Private Limited for 2 years and 4 months. He worked as senior research scientist, deep learning, NLP, deputed at Rico Innovations Private Limited, and he worked there for almost 3 years from 2016 to 19. At present, he is a chief scientist in Safersoft. He started with inventing a money counting machine as an engineering student. He was involved in R&D related with smart, high-level security systems, home automation, etc. from Jan 1997 to September 2002. It's very, I feel privileged to inform you all that he did his B in computer science in our college, that is GhousiaCE College of Engineering. We are very proud of you, Syed Yasin sir. Please take over. Thank you. We warmly welcome you for this 1 week FDP faculty development program. Please continue with your lecture.
Yeah, thank you so much. The pleasure is mine, and it's a great feeling, a heartwarming feeling that it's been almost like 23 years that I've been out of GhousiaCE College, but it looks as if I just left the colleges today. I still have, you know, my mentors, my teachers. I do remember Professor Dr. Zahid Ansari sir. He was so helpful when I was a student there, and I remember Professor Babjan sir. I really appreciate to have a phenomenal mathematical teacher, because AI has a lot of math, and I realized the importance of math once I got into AI. So pretty much of what we have learned in our 10th, 12th, and our engineering is really helpful in the field of AI and anything going forward. Even if you're in electronics, electrical student, your Fourier transforms, Laplace transforms really help a lot in your time series. So what we've learned in engineering, it really helps going forward. So I'm very glad to be the student of GhousiaCE College. I have some very warm memories, and I really appreciate and thank all the teachers, professors, everyone of the college. It's really a great feeling. So let me start with AI. Before that, let me basically show you, kind of give you an elevator pitch, what was designed by Government of India when I won this DST Lockheed Martin Award. This will basically give you the background of my humble work. It's just a 2-minute video, but it will help me as well as you to understand the context of what I'm doing.
To get a better understanding, let's do an actual search using the word abscess, a medical ailment, through a search engine and through Syed Yasin's algorithm. The search engine gave multiple results, whereas the limited results from the algorithm could be read on the same page without opening multiple pages. Latent metonymical analysis and indexing is often confused as a search engine, but the fact is, this technology was designed to supplement the existing search engines to produce better results on searches.
It is a self-learning algorithm, which means it doesn't need any training data to get started. So it basically learns from the data and gives the desired output.
This self-learning algorithm, unlike other search engines, provides the user with a 3-dimensional search-like list of questions and answers, web results, related search, pictures which can be read and accessed on the same page. The related topics on the issue are generated by the algorithm itself. This algorithm takes independent decisions without human effort and efficiently classifies words, builds contextual dictionaries, and provided related searches.
these technology that we are working on is more or less the paradigm shift to search. Today, search brings information. We are looking to bring knowledge apart from just information.
This technology uses a mathematical approach to identify the relationships between words in a set of documents. The inspiring factor for Syed Yasin was the field of artificial intelligence. He kept that as his basis and designed this algorithm not only for search engines, but also for data mining and semantic web. This self-learning algorithm not only makes life simpler, but also research fun.
Okay.
Thank you, Syed Yasin sir.
Yeah, that kind of gives a high-level view of some of the work that I've been involved doing. So going forward, AI, by the way, if you just go through the theory part of it, it's a very dry subject. It's intimidating. The language is different, and people are not very much inspired just by reading a book on AI. AI really gets fascinating, interesting when you start, looking at some of the demos, some of the action that an algorithm or a machine can actually start doing. So we'll start the session with some of the demos so that that kind of intrigues your interest. So we'll get started with demo. I'll be covering a few things that will help one understand machine cognition in the context of where we are today and how the technology is heading forward with respect to AI and machine learning. So let us start a very simple demo. Okay, this is not the one. Yeah. So here we have, today our phones kind of recognize us, they unlock based on facial recognition. So we understand that there is AI behind, but what kind of AI, how it works. We'll just look at some of it with a very high level demo that I'm going to give you now. Now you see here, I have a Python program. I mean, this Python program has implemented an algorithm on AI. And this model is based on CNN, convolution neural networks. And what it does is, it basically has a database. You see one folder called Obama. I have pictures of Obama here. This is the training data, or the ground truth data, as you say, in neural networks. So we're going to create something similar, with respect to my photograph so that the machine can learn. So let me start this.
I am a machine and I need data in order to classify and identify. I am an algorithm that detects and identifies faces. Hence, in order to identify you, I need to take your pictures. Taking your pictures, give some expressions as told, please. Look straight. Look a little toward your right, just a little. Look a little toward your left, just a little. Look a little upwards, just a little. Tilt your head a little toward your right, do not turn, just tilt. Tilt your head a little toward your left, do not turn, just tilt. Smile, please. You did great. You have an incredible smile. Keep smiling and have a nice day.
Now you saw this algorithm kind of, took my pictures. We go back to the database and you see my pictures are taken. Now this is something called ground truth data. What it means is AI needs a lot of data to learn and understand the data components. Now, when you saw that bounding box, that green box that you saw, it's based off edge detection algorithm. That is again another algorithm behind that kind of pre-processes the data, identifying the object of interest. In this case, the object of interest was my face. So exactly there, it has taken the images of me, but has truncated the other aspects of the image. So it has basically chopped off the rest of the image, but only has taken the image which was within the bounding box, which was a green box. So there is a data preparation, data normalization, data capturing. Why do we need this? We need this for the algorithm to learn. So let's go back and see if the algorithm has learned to recognize me. Now this is what happens with our phones and with any device that kind of recognizes us. In image recognition, facial recognition now is a very common technology used highly in surveillance. Now this is how things work.
Face detection algorithm initiated. Give me some time to train and identify the pictures I had earlier taken and let me identify who you are. It took a while for me to learn from the data. The GPU machine would have helped me learn faster. Nonetheless, I am ready to recognize. Don't be surprised if I mess up. After all, we all make mistakes sometimes. Hello, Syed.
You see, it's kind of struggling to identify. If I go a little closer, it's kind of recognizing me, say at 64%, 63%. Now, what if I bring someone who is also trained to recognize, like this person?
Hello, Obama.
Now, can it recognize both of us? You see the bounding box and you see that facial recognition. The bounding box, as I said, is basis of edge detection algorithm. It basically tries to identify object of interest. That is how machines see, and that is how they recognize. It's a bunch of pixels that the image kind of image processing algorithms work, and then they kind of classify, recognize that basis these features. This is Syed, this is Obama, this is a car, this is a sheep, this is that, this is this. I'm going to show you more of it now.
Syed.
So now what you're going to do is, now you know what you saw right now is you saw how a machine kind of captures data, learns from the data, and then kind of identifies, what the picture is or who the person is, things like that. Now also we'll extend this to identifying if a machine can identify objects. Now this is very imperative and important with respect to self-driving cars, robots that can actually see, recognize. We see a lot of these things in the industry today. So I thought this will very much connect you to understand that, what's going behind the scenes. Now, the algorithm that we're going to run is based off a single shot detection. SSD is what they call, based off an image. This algorithm, which is based on Caffe model, like you have a TensorFlow framework, you have Keras, you also have a Caffe model, which is a CNN model, which is specialized to and designed to identify objects within an image. This also works on edge detection to basically understand the object of interest and then identifies or classifies what a particular image is. Now you see we have a bunch of images here. We probably take this example 1. Okay. Yeah, so example 1. You see this image that we saw here, example 1. It has identified as car 97, car 99%. Now that's how robots identify objects. Now again, you see this bounding box. This is an object of interest based off edge detection algorithm, and it kind of understands. It is classifying from this entire image what a car is. Now this is a classification cluster for a car. It's kind of clustering pixels and identifying, okay, this bunch of pixels that I see here within this bounding box represents car. That's how it's classifying. Now we'll do something similar for maybe a horse. Maybe this image that you see here. Horses. 2. Okay. You see, 100%. It's a horse. Now, Let's go with this horses one. I'm going to show you where AI kind of fails. This is a good use case. It all depends on the data, and it also depends on the training. I mean, data represents your ground truth. It depends, and it basically represents the kind of training you have given to the model. When you see this horse, this picture, you have a bunch of horses here, but it is not able to identify horse. It has identified this as bird, this as person, this as person. It has identified things, but nothing like a horse. So this is where AI kind of fails. You have to be very careful when you train the model, because if this is something that you will see in your unseen data, and if you're not trained on it, AI will not classify it because it has not learned that particular scenario. Let's take this example 5. We have many people, a bunch of objects here. Example 5. You see, it's a person, 88%, horse, 99%, dog, 60 some percent, car, 99%. And you see a person standing behind, it has not created a bounding box to this. So there is a threshold basis of which the algorithm will create a bounding box and detect the particular object. So you have multiple objects, so a machine can actually identify multiple objects within a scene. Now, make this dynamic. This is based off single shot detection. Make this dynamic and apply that in self-driving cars. So at a time, these the dynamic aspect of what you saw in image recognition that we ran earlier is the same. So it dynamically keeps identifying, and the percentages keeps going up and down when you're actually driving a car, when the car is actually driving itself. So you saw, this algorithm trying to identify, recognize various objects. Will run one more. Lastly, maybe a sheepdog which looks like a sheep but actually is a dog. Can it identify a sheepdog? Yes, it does. It's a dog, 99.99%. So that's pretty impressive, having this model kind of work. Now, what we've seen is we basically saw image processing. You see this cute child here, it's image processing. And we saw some of the speech where we saw machine talking to us, it was communicating in certain way. And there is language processing, NLP. I specialize in NLP. I also do image processing, but NLP is my specialization. Let's go here to see if machines, if they can understand documents and the language that we speak. Okay, let me take you through a demo. This will help you understand how a human classifies and how a machine classifies. Now, if you have a basket of vegetables, fruits, and toys, for a human to basically identify, understand that, he has to kind of learn them. So as a child, we all have learned to recognize what a fruit is, what a toy is. Remember the books that we studied in our nursery, in our LKG, UKG, first standard? We used to have this kind of images of fruits, vegetables, toys. So humans use their intelligence to gain knowledge via learning. And of course, we have guidance, the teacher, professors. And with that, we basically classify, okay, these are toys, these are fruits, these are vegetables. Now, that's got to do with how we do things. Now, let's do the same with documents. Documents on vegetables, documents on fruits, documents on toys. And let's build an algorithm. So I developed an algorithm called LMI, Latent Metonymical Analysis and Indexing. This is an unsupervised machine learning or advanced machine learning algorithm that learns from the data itself by decomposing the data. Fortunately, this algorithm was also awarded a gold medal at a national level in Lockheed Martin DST Lockheed Martin Innovation Competition in 2009. And if we give these documents to this algorithm kind of decomposes based of intelligence. Intelligence is basically the algorithm that's running behind. It kind of learns from the data itself and then builds clusters of vegetables, fruits, and toys, and puts those words in those clusters like irrigation, farming, vitamins, manure, vitamins, food supplements, entertainment, child psychology, so on and so forth. And when you add more documents, like say you add incremental index of say fruits, and it kind of decomposes a few words like juice and antioxidants and incrementally increments the relevant clusters. And similarly, you add more documents on animal, it kind of finds those words, basis decomposition technique, creates a new cluster animal because it was that animal cluster was not there. So it kind of incrementally indexes it. Now, what is the use case of such a thing? Let me go here and let me, Google is all about NLP, natural language processing. I mean, now Google has got into, AI in general. So let's take a use case called heart attack. Now you see, we have these bunch of results. Typically, when we talk about natural language processing, most of the NLP that we see around with respect to search engines is based off inverted index. A vector space model is hugely used. So we have learned vectors in college, but never kind of understood the real world application of vector space model. But search engines is all based on vector space models. So people who really understood multidimensionality and vectors, they can really connect to this aspect of how a search engine kind of works. Now, when you see a heart attack, you see some knowledge which Google is bringing from, in this section from Apollo hospitals. What I want to actually show you is this part where Google brings related searches. You see this. Now, I basically showed you this algorithm, how it kind of clusters the related words all by itself. So this is applied into this search engine. If I put in heart attack here, Medwin belongs to, it's developed by myself sometime back in 2009-10. It's an empirical, testing search engine. It's not a production search, which is why you don't get to see this. It's an experimental model. But that algorithm is patented and it kind of demonstrates how this algorithm works. So when you see a heart attack here, you get chest pain, coronary artery disease, cardiogenic shock, just like this demo that you saw. These are the clusters, and these are the clusters for heart attack. And you have a bunch of clusters here. So and Google gets these as related searches for heart attack. But more importantly, what this algorithm does is, there is another algorithm called LPSR, latent precise extraction and synecdoche representation. Even that is a patented algorithm that brings a second dimensional search, which is a knowledge space that explains why chest pain and heart attack are related. Now, this feature is not there in any search engine today. I was basically on an entrepreneurial pursuit to build a new search engine based off this model where search will be more towards knowledge gathering as opposed to information retrieval. So here you see more of knowledge. A person who has no idea what a heart attack is gets to know the entirety of heart attack with this kind of knowledge snippets that are kind of presented, like acute coronary syndrome. As a layman, might not have any idea of what that is, but when I read the sentence here, I get to understand that acute coronary syndrome is a term used for any condition brought on by sudden reduced flow to the heart. And that's how it's related to heart attack. Similarly with cardiogenic shock. And so education by itself can have a huge impact by this kind of technology where you type in a search query like strabismus, and it kind of gets me the knowledge here. I read everything from the search page itself. I don't have to kind of click the link, go to the content page. So you see this question and answers. Google does bring those here. They started off in 2015 or so. This prototype was built in 2010, and you have symptoms here. And you have web results like how Google does, but when you click on this, you have an auto summary, you have keywords automatically found. So you pretty much read the content page, which is summarized here. So you get knowledge. So with NLP, you do a lot of that stuff. That's the idea of why I presented. So now you know a machine can speak, a machine can also listen and understand. I worked on a project sometime back in 2000. Let me open this. 2003. Developed a prototype for using speech engines where a machine kind of can talk and also listen and carry out orders that are given to it. Just let me see if it's opening. Yeah, it has opened. This one, this is the PC response to your voice command. This was in 2004. So this is much of like what Alexa does. You speak to a computer. I mean, Alexa speaks back, does what it is told. That's what it is. So going back to this presentation, we know a machine can talk, speak, listen, carry out orders. A machine can see, recognize objects. A machine can also understand language as well as documents. We just saw a demo for that. So much of what we do is pretty much what a machine is also trained to do these days, but in isolation. You have speech technology in isolation. You have image technology in isolation. You have NLP in isolation. They're all isolated. But each of these things, we do it. We do see, recognize things. We do talk, understand. We also read documents, understand. At some level, machine is able to do much of this. That's where technology is there today with respect to AI. So where are we heading? So getting back to AI as a definition, now you know, since I hope there is some interest created on AI, going through those demos, you might be also interested to know the definition of AI. Usually book starts with this definition, and that makes so boring because we are not able to connect what that actually means. So in science engineering of making intelligent machines, we just saw intelligent machines, and this kind of helps us connect. So like it or not, we are heading towards this. The scary thing about AI is not regulated, which is why recently Sundar Pichai of Google was insisting that AI has to be regulated, because Google itself was in some kind of complexity because they were using their AI for drone, and many of Google's employees kind of opposed that. He said the AI cannot be used for military purposes, and then Google had to kind of back off the project which they had been working with collaboration with Pentagon. It was a big project. It was all over the news. So AI has to be regulated because these machines, they get smarter. They can see, they can recognize, they can talk like us. They can read documents, they can understand. If you bring AI all together, not in isolation, if you bring all these three things together and you encapsulate these three things using AGI, artificial general intelligence, which is the future of AI, the next step in AI is artificial general intelligence. We are moving more towards logic. Logic. Right now we have a lot of math, but logic is something which is very difficult to comprehend with respect to a machine. Much of what we do it very easily. It's very difficult for one to actually develop an algorithm for a machine to do it. But there is research that is happening in the context of AGI, artificial general intelligence. OpenAI is doing a lot of research on that. Microsoft is backing their research. It's just a matter of time that we have AGI and you see operating systems for robots like this. Now robots, typically what we have seen robots like in a SEMO robot, we basically think if a machine can walk, jump, and do things that we do, it's a robot. That is a structural aspect of robot. A robot can walk. There is a lot of research and advancements that has been done in gyrodynamics. Now, gyroscopy technology is a solved problem, which is why SpaceX is launching rockets, and these rockets are kind of, putting the satellites in space, coming back, docking themselves back to the station, landing all by themselves using this gyroscopy technology. I mean, this gyroscopy technology kind of helps machine balance themselves. Boston Dynamics, which is one of the, leaders. Boston Dynamics, earlier it was a Google's technology, which was later bought by Boston Dynamics. And this company, they have robots that can balance themselves so well that if you push these robots, they balance back themselves. They do somersaults, they run, they jump, they do all sorts of things. You can Google this up. There are a bunch of videos in YouTube. You can watch those. If you type in Boston Dynamics, you get a bunch of robot videos. You watch them. So you have, this technology, structural aspects of a robot is a solved technology today. But what is not solved is a logical aspect of reasoning within the robot. So going forward, you will have operating systems for robot. And that is where you'll bundle these three things into one and make it more intelligent, make it more look intelligent. So you'll be having operating systems specific for security, specific for maybe farming, doing a specific task. You may have robots of all sorts of things. So it's a flavor of operating system, just like Microsoft Office. You have Word, you have Excel, you have Microsoft PowerPoint, you have so many things. You will have these kind of flavors in AI. And AI, and when you have this kind of technologies coming up, AI will be scattered in almost all the fields. That's where we are. And before we go there, as I said, with this kind of technology, it is definitely a risk to humans if AI is not regulated. So having AI to be regulated is a very crucial thing going forward. And AI is a very vast subject. It's a very deep subject. What I have learned from AI so far, I was first introduced to AI in 97 is when I got first introduced to AI, and I was really fascinated by what AI can actually do. But what I've realized is, what I've learned so far of AI is very, very little, very tiny. And I've realized that knowledge really humbles one. You learn so much and you realize that there is so much more that you have to learn. And what you know is very little. So the essence of knowledge is to humble oneself. And AI is no different. If you get into AI, it takes a lifetime for a person to actually get a decent hang of any of these branches. Like if you're getting an NLP, natural language processing, it takes a lifetime. And trust me, even if you're there in this field for many years, what you would know is very little. So AI is ever learning. You keep learning. There is no stop to learning. So if you enjoy to learn things, then you will really enjoy AI. So we have natural language processing. We saw some of this. We saw some demos on this. We saw some of speech. AI started off with expert systems. These are legacy systems. People used to build inferential engines based off this. I started off with expert systems. The speech technology that I developed, which I showed you, a paper clipping that was based off expert systems. And you also saw some of the demos on vision, image recognition, machine vision. Planning, I'm working on a project which is based off planning. It basically simulates, it learns from how a human planner plans and then understands those patterns and applies for future forecasting. So planning is a huge domain by itself. So I'm currently working on one of the projects on planning. Robotics does have AI, but the scope of AI that I told you is balancing and basically having a structure of a robot by itself. It has some of the mathematical models in context of gyroscope. But if you club robotics with vision, speech, natural language processing, you have all this technology, but in bits and pieces. If you club them together, there is a disruptive technology that you will come up with. Just like iPhone was a disruptive technology way back in 2006 and 7, you will have this kind of disruptive technology, which is the robots that I was talking about going forward. These may come off maybe 2-3 years down the line. And then, with natural language processing, you have text generation, question answering, context extraction, classification. You saw classification example. You also saw question answering. Machine translation is something that you will see in Google Translate. So this is a very high level AI tree. Okay. Oh, why did I close that? And then, yeah, this is AI in its true sense. We saw vision, we saw speech, we saw natural language processing. Logic is somewhere we are getting to with respect to AGI, artificial general intelligence. Now that is complex, but there is a lot of research that has been done on that particular subject. But if you have that logic, then you're creating a very smart machine going forward. So there are questions like, is AI glorified statistics? Well, the answer to that is true. AI works basis statistics. If there is no data, there is no statistics. If there is no statistics, I mean, a machine can't learn anything. So for algorithms to learn, they need a lot of data, particularly with deep learning. You need lots and lots of data, which is the reason why there are many articles on the web that you see that data is the next oil. People kind of exaggerate, kind of try to correlate data with oil. That makes sense to a certain extent. But yeah, people do exaggerate, but yes, data is very valuable. People today, companies today offer services free in return of data, which is why privacy rules and acts are being imposed on companies like Facebook and Google, because they give their so many technologies for free, but internally they are using our data because data is valuable. It's very, very important, because without data, you can't build any AI on top of them. This debate on AI and machine learning, I always encounter this, particularly with people who start off with AI. They love kind of debating on this. They kind of say, what is the difference between AI and machine learning? AI in general sense is more like a superset, I would say. It's in simple, it is to make machines intelligent. Machine learning is more towards the practical implementation of AI. That's how I see. I mean, it's a subjective definition. So people can argue on this. Sometimes people also argue that, why do we call AI AI? Why don't we just call it an algorithm? 3 decades ago, AI was not much heard of. The only thing that was heard of was a Turing test. And that said, if a machine can simulate a human intelligence and the other human being cannot identify whether it's a machine or human, then you pass the Turing test. So people even today argue, what do you even call AI as AI? Why don't you just call it as an algorithm? So when you get into this kind of philosophical or discussions, I usually don't waste my time. I basically nudge that discussion and say, whatever you feel best, you go with that. I don't have any conflicts. But the debate continues. People try to argue on this, and most of the time, people who have less knowledge, they argue on this. I mean, this is what I've noted. People who really understand AI, they rather spend their time writing an algorithm and solving a real world problem. But people who don't know much of AI and machine learning, they enjoy arguing on this, giving an impression that they know a lot about AI. And that kind of intimidates someone who knows AI to listen to. Now, there are some high-level classifications on the type of machine learning one can get into. Majorly, machine learning can be supervised. The first demo that we saw is a supervised machine learning, where we train the machine that this is Syed, this is Barack Obama, and you identify these two people, and then that's how a machine kind of learns. That's supervised learning. The unsupervised machine learning, we saw that LMI demo, where the machine is given a bunch of documents, but it has not been trained to identify what words belong to what cluster. So the algorithm kind of decomposes the data and builds clusters on its own, and kind of incrementally adds words into those clusters all by itself, one after another. And then there is also called as reinforced machine learning. This is used primarily, in self-driven cars, where any mistake that is done by the model is rectified probably with an external force or external input. And then the machine knows, okay, this is the mistake I did last time. I'm not supposed to repeat that. So it keeps incrementally learning. It makes mistakes, but then it learns not to make that mistake again. So that's reinforcement learning. So this is used in many areas, and you might have also heard of deep learning. So what is the difference between deep learning and typical learning with respect to, say, if you're using a neural network to train on a certain data, if you're creating that kind of a model, where does deep learning actually come in? See, if you're using a neural network, which is typical of supervised machine learning, you have a training data, but if you overtrain a machine, you will overgeneralize. We'll get to generalization in the next slide. In the next few slides, we'll get to generalization, what it actually means. So what it means is you will, if you overgeneralize, then the machine will misclassify. It will not be able to identify or classify things effectively. And that is where the drawback is with neural networks. With deep learning models, the advantage is the more the data you give, the better the performance of learning. So the machine keeps learning, it doesn't get saturated. So this older algorithm, you see the red curve, the red line. So they used to get saturated. You can't train the model more, although you have data. So that was a disadvantage. With deep learning, the more the data you give, the better the performance it gives. We'll get to what generalization is in this slide, but before that, we'll touch upon a neural network at a very high level. So a neural network, you can visualize this as a graph theory. You have a bunch of nodes, you have edges. These nodes connect each other. Every node can connect to every other node. It depends on the kind of architecture you want to basically imply or design. You have a bunch of hidden layers. You have an output layer, input layer. In a nutshell, typically if you open a book, they explain neural network to be some form of a neuron, a perceptron concept, and the first few words will intimidate you and you will lose the focus of where you're heading. Typically, the example given with neural network is using neurons, because neurons, every neuron in our brain is connected to every other neuron. And there is inbuilt mechanism within our brain, basis of which a bunch of neurons get triggered, and that's how we make decisions. That's the philosophy behind how our brain works. So something similar is being used to replicate a human intelligence. That is why they call this as a neural network. But that's how people kind of visualize that is there as is. You may appreciate it, you may argue of why they have put things like that, but you can visualize a neural network at a high level as a complex die. This die, I would call it as an overfitting model, because whatever you put in this into this die will give the similar output. It's a die, mechanical die, a die cast. You put molten iron, it'll basically churn out the same model that is here. With neural network, it is also a die, but I said it's a complex die. A die can basically always infer or get one thing out, but neural network can do such things of multiple magnitudes. It's like it can identify, if you're training a model in numbers to identify handwritten numbers 0 to 9, so there are totally 10 clusters of identification. Like it can identify 1, it can identify 2, it can identify 3, so on and so forth. But how does it do that is basically within this hidden layer, there are a bunch of weights. Weights are basically numbers from -1 to 1. And once you train the model, those numbers kind of get distributed within these weights. And when you pass in 1 here, that particular output layer will give a corresponding value of say 0.99. So the higher the value, that means the machine has classified that particular input to be inferring to that output. So this is much of theory. It's very difficult to comprehend. If I had time, I would have actually showed you a demo on how this neural network kind of works. But maybe we'll take that because neural network by itself will take a bunch of hours for one to understand, comprehend. Even for me to kind of explain this, it'll at least take me like 1 or 2 hours, for you to understand how things work internally. So, but I'm not doing justice for explaining how neural network works with some of the definitions and some of the explanations that I gave. I do understand that much of what I said, you may not be able to get it. But for the time being, understand that neural network is a complex die. It kind of, there are a bunch of weights and they get distributed and you kind of infer input to output. Generalization is basically like say we have a human being writing 1 in a certain way, the human writing 1 in another way, but a bunch of people writing ones, handwritten digit 1 in different ways. And there is one more person, and if you train this machine to identify all those ones, and it understands only those ones, then it is overfitting the model. It means if someone else write, like say 10 people have written 1, now 11th person comes and write 1 in his own way. Now the machine will not be able to classify that 1 as 1 because it is overfitting model. That is why we need generalization. Generalization is the magnitude of learning. It's basically how much your algorithm has learned. So if you've done proper generalization, a machine can also identify that 11th one, which is written by a human, which is not trained earlier. It will identify even that as 1. That is how generalization kind of works. So this actually is very important when you're working with neural network models. You have to take care of many of these parameters. But for the time being, just remember these words, I would say, or jargons. I know it's very difficult to comprehend within 5-10 minutes. Okay, so algorithms and their fancy names. If you're getting into AI, try to understand these algorithms deeply. I've come across people who say that I have read all the algorithms in AI and with confidence, as if they've understood everything. Trust me, I have worked on Bayesian probability for more than 1.5 years on a very complex problem. And if you ask me about Bayesian probability today, I would say what I know about Bayesian probability is very little. These algorithms might take you to 20 minutes to read, but that's just to read. To understand, it takes a very long time. Just to understand support vector machines, to understand the complexity of SVM, the kernel trick, which is the essence of SVM, trust me, it will take not less than 6 months. If someone comes and tells me I read SVM and I understood, he hasn't understood anything. That's how I see, because in the field I understand understanding these algorithms is difficult. Applying them in solving real world problems is even more difficult. And much of what these algorithms are doing is the essence of linear algebra. We took linear algebra for granted as students, but these algorithms are all based off linear algebra. The more you understand the dimensionalities, the vectors, the vector space model, the classes, the span of a vector, the transformations that you actually do, the matrix transformations, you will appreciate matrix. I was like, who invented matrix? I mean, such a wonderful guy. Without matrix, you could not solve much of these problems. So you'll appreciate the math only when you understand, when you see algorithms based off this solving problems. Like you see this SVD, singular value decomposition. This is a semantic. I mean, this algorithm is used in almost every space. It's used in space exploration. It's used in astronomy. It's used in electrical engineering. It's used in building bridges. It's used in almost everywhere. It's also used to build semantic web. TOEFL exam was passed by these algorithms, latent semantic analysis and indexing, and these are based off singular value decomposition. You also have principal component analysis. And these algorithms are based off eigenvalues, eigenvectors. These are vector space models, as I was mentioning. So once you get into this, you will understand what a principal component is. Right now, these jargons may intimidate you, like this is too complex. But if you've understood linear algebra very well, understanding these algorithms will be much easier and simpler. So if you want to get into AI, please get into these algorithms, understand them well. It'll take a long time for you to understand, but once you've understood one algorithm, then understanding the rest will be easier. And that gives you a lot of confidence, because you will start to appreciate the math behind, you will start to understand the math behind, and that will give you confidence. And once you understand the math behind, you will also understand how to apply and how to think mathematically with respect to solving real world problems. So the best part, math, this equation might intimidate you. This is a shallow network, neural network, back propagation equation. It's a cost function. Actually, it's a activation function. I'm sorry. You see this E, you'll appreciate all these concepts. Euler's constant. There is a reason why that is used in math. So the math that you have to kind of look into is, as I said, linear algebra, nonlinear calculus is used for optimization. Particularly if you're using neural networks, you may want to understand calculus, because you'll be using gradient descent, and gradient descent, based off calculus, you'll be looking into global minima, local minima, all those kind of things. And matrices is important because you'll be trying to comprehend multidimensionality based off matrices. You'll be using a lot of matrices. Without matrices, it's very difficult to solve these things. You'll be using a lot of statistics, because AI is built on statistics. As I said earlier, it's based off, it's nothing but glorified statistics. And probability theory, you saw the demos that earlier, it was giving 99%, 63%. So machine will make a judgment, and the judgment will have a value of how much confident a machine is. So it all boils down to probability theory. So this is the math, the essential math that one has to really understand well. And then we get into some of the frameworks. These frameworks, Python has been very popular. I've been working using Java for a very long time because we didn't have Python then. I used to work in C a lot, and assembly programming, and then Visual Basic, and then Java. I really loved Java for a very long time because they were very strong string operations since I was working on NLP. So Java actually gave a huge bunch of string operations. So I was like obsessed with Java. But when I started working on R and Python, I really appreciated them because much of the algorithms that you saw here, like say support vector machines and singular value decomposition, if I have to code this in Java, the complexity, the math is so complex. To implement the math in Java would easily take a long time, maybe 2-3 months for me to code SVD if I have to do it manually using Java technology. Much of that is just one line of code in Python. Where did I lose that? Okay. So these languages really help. So if you want to get into AI, Python and R for data science, this slide is 2 years old, so ignore this. I think Python has gone up. Java, I don't know where Java is today, but in a nutshell, these are the programming languages, much of what are used. So it really helps. Python to implement SVD is a single line of code in Python and R, even R. But you have to know how this kind of works so that you implement using Python or R language. So you have to know the math behind these algorithms as well. I lost a slide. Okay, nonetheless. Work2Vec is a very recent NLP framework for natural language processing, identifying the semantics and relationship between words. TensorFlow is good based off, Python. It's a framework. It's optimized framework. So if you're writing a neural network program manually and you write the same in TensorFlow, TensorFlow offers a lot of abstraction. You will be abstracted with a lot of complexities. The back propagation and all those things will be taken care of TensorFlow. But if you're writing a neural network on your own, you have to do all the math on your own. And that becomes very complex and complicated for you to implement the model. That's where libraries like TensorFlow or frameworks like TensorFlow really help. Keras is another framework on TensorFlow particularly for image and object detection. You also have Google Speech. You can see some of these frameworks prominently used today in the market. These are the programming languages we're talking about. And AI and IT. So do we stop here, or do you want to also see this? This basically covers how AI and IT work in the future for a software developer and tester. So usually I touch upon this for people who are software developers and they want to upskill themselves into AI. I basically run this session on big data, IoT going forward for them. So do you want this, or do we stop here so that I take some questions?
Hello, participants. Participants, can you hear me? Hello?
All of them are on mute.
Hello, sir.
I think they can actually put questions in the chat box.
Ask himself to continue.
They can put questions in chat box so that Zoom doesn't crash.
You can continue for some more time, Yasin sir.
Okay.
I
I hope I didn't put the
your,
audience to sleep. Okay. See, with respect to how IT and AI is going forward,
Excuse me, sir. One question is there from Mr. Krishna Prasad.
tell
The
me,
question
sir.
is, sir, can you throw some light on MATLAB and deep learning, please?
Okay. So I think with respect to MATLAB, I may not be the right person because I haven't worked on MATLAB. I've worked on, Python, Java, R, C, C++, assembly programming, bunch of databases. I worked more on inverted index using, since I was in NLP. So multidimensionality and vector space models is my humble specialization. So since MATLAB was a luxury and it costed a lot of money to get the license, I didn't get a luxury to use actually MATLAB, but now I'm glad that we have libraries like Python and R. So you can use MATLAB. Much of what MATLAB can do, I think Python libraries and R libraries are offering that. So if you are having a specific question of where you want to get with MATLAB, I can basically try to connect you to how you can do that in Python maybe. Hello.
hello, Krishna Prasad.
Okay.
Hello, Krishna Prasad. Can you hear me?
It's about
Yeah,
IC engine and it,
IC engine and its analysis.
Okay.
he says that, yeah.
IC engine and its analysis. You want to use MATLAB for this? Yeah, I think some of our folks have used MATLAB. I don't know if Dr. Saif has used MATLAB. He may be able to kind of guide you on this. Since I haven't used MATLAB predominantly, then I may not be the right person to answer that.
Okay. So shall we conclude, or anybody wants SCN to continue? Hello, dear participants.
Yeah, tell me one more question. Yeah, he's kind of writing the questions in the chat box.
Yes.
No questions from, okay.
Unmute yourself. Unmute yourself and ask the question directly.
Okay, convolutional neural networks. If you want to use CNN model, then you can have a look into a CAFE model that I actually gave based off convolutional neural networks. By itself is a very vast field where currently the trend using image processing is semantic segmentation. So image processing has actually gone the next level of semantic segmentation. And for you to have a deep understanding on CNN models, you probably need to read a lot on, papers written on CAFE model. CAFE model, you primarily look into that because that model is really done a lot of, work on CNN because the company that I was working earlier using CAFE for image processing, and the results were pretty accurate. TensorFlow does also offer. So CNN, you have any specific question on CNN? You want to get to know the decomposition of how a CNN model kind of decomposes the image to basically split them using stride and all that? It's architecture. Okay. To get into the architecture of CNN by itself will take a long time because to understand the complexity of how a CNN works, it basically kind of decomposes an image. like we do this decomposition technique in natural language processing. We decompose the document to basically extract the principal components and then work on it. So similarly, you know, for a CNN, you take an image, you decompose that image, and then you work on the snippets, and every snippet will have certain weightages, or it's trained earlier to identify that part of image. And that's how you basically integrate them all to understand what that image actually is reflecting. And that is the exact demo that we saw earlier of how a machine is able to identify an object or multiple objects within an image. So that's where a CNN actually is very powerful. So if you want to get into the architecture of how it works, it is complex. And you may have to learn a bunch of documents which are there on the web, white papers, typically written by Stanford or MIT Institute. You can also refer some of the books on CNN, convolution neural networks. Probably you'll get to understand a little better, but trust me, the more you actually get into CNN, you will be able to architect it efficiently. The difficulty in the architecture is to basically define how many layers you want to have. As your layers will increase, the complexity will increase. So every layer will identify a certain feature. So that's how it is. If you have a complex image, like for the images where we saw a machine, an algorithm identifying a person, a horse, a dog, a car, that's based off a very complex CNN model where you have multiple layers and each layer identifying a certain object. So the more the objects you want to identify, the more complex the architecture gets. And you have to kind of draw a line because managing them, maintaining them also becomes a huge task. So if you are intrigued with the architecture, I'm very happy for you because you know, you asked a very advanced question. I think you should get into image processing and this will really help you. But there's a lot of learning that you have to do, and you'll be able to understand the complexities of the architecture and how things work out based on a lot of empirical analysis. And usually you need a GPU to run these models. So there's a lot of computing power as well that is required to test an architecture. I don't have any information on the free ebooks, but you can always Google them. But specifically, you know, I haven't used CNNs much apart from the image processing demos that I showed you. What I've used is advanced machine learning algorithms to solve certain specific image processing problems. So you can definitely Google for free ebooks, but more importantly, refer to some of the white papers that are written on CNN, because if you read about GANs, GANs, generative adversarial neural networks, there is so much of work that has been done. You'd probably appreciate the GANs as well. You have CNNs, you also have GANs, so refer to that as well.
Hello, any more questions? Hello?
I'm on LinkedIn. If you can connect me through LinkedIn, some of you have asked for my email. I guess you have my LinkedIn profile. You can just type inside Yasin artificial intelligence in Google. You will probably get my link. You can kind of connect me on LinkedIn. I do help, you know, what you call students to basically, if they want some guidance to get into a specific field with respect to AI, I usually enjoy guiding them. So you can kind of.
Shall we conclude?
Yeah, I mean, it depends on you. I have another half an hour if you want me to continue.
Yes, participants. Hello.
So you just type this, connect me through LinkedIn, and I will answer your queries.
Okay. So let me conclude. So we thank our guests as well as our alumni. Yasin, I feel very proud to say that Yasin was his alumni. He has used to AI waivers. So we were not knowing about idli, kharabat, chochobat, roti, biryani, fushka. We were not knowing all those things. We were knowing only about AI. AI we were not knowing. So introduced us to deep learning, natural learning, expert systems, speech, vision, planning, robotics, speech to text, speech to text to speech. All these flavors he has introduced us to. So we were knowing about only AI, we were not knowing about AGI, Artificial General Intelligence. I thank all the participants. I thank Dr. Saif Abrar, who has enabled this FDP to happen through this his unlimited time Zoom ID. I thank one and all. I thank our HOD and all my colleagues who have been supportive in organizing this. Free to Hello.
Thank you so much. The pleasure is mine. I really appreciate your time. I hope this session was helpful, and my humble regards to all the teachers and professors of Ghaousia College. I truly remember you all, and do pray for me. I'm still a student. I have a long journey. I have to learn a lot of things. So even I am learning. You know, all I can say is do remember me in your prayers.
To continue and come out with more success and proud to say that it has Thank you very much.
Hello, the voice was not clear.
Anyways, thank you, Yasin sir. Thank you very much for your precious time. And no, it's really a big opportunity. And one request from your side, for you is that, if possible, your time can be spared. You can give us more insight on artificial intelligence in application to electrical engineering and all, if possible, in future as well.
Inshallah, I will try that. Inshallah.
Okay, thank you everyone for joining us. Let's meet tomorrow for the next session. Thanks a lot. So now we will be ending the session. Thank you everyone. Goodbye. Good day. Take care.
Thank you. Thank you so much, everybody. Bye.